Hi everyone, my name is Mark Hodson. I'm a systems and software engineer at Righty. In this presentation, I'll give you a tour of solving constraint satisfaction problems on Righetti's quantum hardware. Righty is a full-stack quantum computing company based in California. We have subsidiaries in the UK and Australia, and I work remotely from Adelaide. We design and build superconducting quantum processors, or QPUs, in our own captive foundry, and we make these available through our Quantum Cloud Services platform and through Amazon Braket, which is part of Amazon Web Services. This is our fabrication facility located in Fremont, where you can see clean rooms and equipment for processing wafers. And this is our quantum computing facility located in Berkeley, where you can see several blue force dilution refrigerators that host QPUs under test and those that are deployed to Quantum Cloud Services. Our current system on Quantum Cloud Services is called Aspen 9. It's a 32-qubit processor with a topology of interconnected octagons, and it's fabricated from a single quantum integrated circuit. That is, it's fabricated as a single silicon wafer supporting the superconducting Josephson junctions and other components that make up the QPU. Our next quantum processor will be 80 qubits, is anticipated for release in early 2022, and it's based on a modular interconnect technology that lets us couple multiple quantum integrated circuits together, solving one of the challenges of yield and scale for these devices. Our approach to system development is one of hardware-software co-design. Applications are a critical part of this. Applications sit at the top of the quantum computing value chain, and they're the lens through which we talk about quantum advantage. I'd like to thank the organisers of QCP 2021 for inviting me to give this talk, as optimization problems feature in much of our collaborative R&D. We'd be interested to partner with experts in classical optimization as part of our portfolio approach to quantum advantage and work on projects that are of mutual benefit. This presentation is divided into 4 sections and includes a demonstration of solving max-cut problems on the Righty Aspen 9 QPU. The scope of this presentation is on binary decision variable optimization, which includes problems like constraint satisfaction. Constrained optimization problems are of real interest to the quantum computing community, as is evident in our work under the DARPA ONISC program. Some of the work presented today is based on publications made with the support of the DARPA Project Office. Above all, as we go through this presentation, I hope to paint a picture of what really happens on our hardware. So, quantum computers for constraint solving. There are 2 main types of quantum hardware that can approach these binary optimization problems: quantum annealers and quantum computers. Quantum annealers have a hardware control system that implements a specific algorithm, and that algorithm can target unconstrained, quadratic, binary optimization problems. In these machines, you can program the coefficients of the input problem, but you have limited control over the algorithm. Quantum computers are digitally controlled and will run any algorithm you tell them to. But not just any algorithm, any quantum algorithm. As far back as 1985, David Deutsch showed that the Church-Turing hypothesis does not describe quantum computation, and so the concept of a quantum Turing machine was born. This has been the foundation of theoretical proofs for why quantum algorithms can outperform classical algorithms for certain tasks when realized on a sufficiently capable quantum computer. To date, we have quantum algorithms running on quantum computers that can target constrained and unconstrained polynomial binary optimization. Of course, these more capable machines are also harder to build. As an engineer surrounded by quantum physicists, I fondly refer to this as the no free lunch theorem. I said before that quantum computers are digitally controlled, and that is true. But unlike digital computers, where the assembly language, arithmetic and logical operations have been so perfected over decades that we forget that there's any electrical currents flowing, Quantum computers are far from perfect, and so the analog domain is very much a place where we play when we're programming them. We can draw a program for a quantum computer as a quantum circuit, like you see here. At the beginning, we wait for the system to relax to the ground state, which means all the qubits are in their zero state. We then apply quantum gates, which modify the state of the system in place, which you see here in teal and purple. Finally, we measure the system to extract a probabilistic sample of the quantum state as classical bits. The information within this quantum system is only retained, on average, for a time known as the coherence time. The entire process of applying gates and measuring out must generally occur within this time. For our current processing units, this is in the order of tens of microseconds. If we do nothing for a time much greater than the coherence time, then the system will relax back to its ground state, where all the qubits are zero. So we can use this to initialize the state, or we can actively drive the state to zero and run successive circuits much faster, which is a process that we call active qubit reset. On our QPUs, gates use DC flux and RF microwave signals sent from the control system down into the dilution refrigerator to act upon the qubit in a specific way. These gates create entangled quantum states and is where the source of computational power comes from. Measurement is similar. A signal is sent into the fridge, it interacts a readout line with the quantum system, and the return signal can be interpreted as a 0 or 1. So a single circuit execution returns only 32 bits of information from our 32-qubit ASP9 processor. But in most cases, we need thousands or millions of runs to complete a run of a quantum algorithm, and we'll show why that is for optimization algorithms in the next section. If I was to describe the capabilities of a quantum computer to solve an optimization problem, it would be like this. Quantum computers can minimize the Ising model cost function you see here, which is an unconstrained binary quadratic optimization problem in the domain of the reals, and where the solution is a length n vector S, whose elements can take on possible values plus or minus 1. We call these spin variables, consistent with the terminology of the Ising spin glass and the terminology of the underlying quantum systems. The lowest possible resource requirements are for cases where the problem matches the edge connectivity of the QPU. All quantum computers have qubits supporting 1-qubit gates and edges that define where 2-qubit gates can interact them, and a problem natively matching this topology will have the lowest gate count and the most performant implementation. From this baseline, you can add advanced gates that extend this resource efficiency at least to 3 body terms by supporting 3-qubit gates. In the last section of this presentation, I'll show you our first 3-qubit gate that does this. Beyond these native problems, we need additional quantum resources, principally in the number of gates used. Gate decompositions let us solve problems with interactions that are beyond the interactions of natively supported gates. We can see here an equivalent sequence of 2-qubit gates that implements a 3-qubit operation. In general, any high-order interaction can be realized on a quantum computer given enough gates. So too, swap networks let us solve problems whose interactions don't map directly to the edge topology of the quantum processor. Swaps are gates that move the variables around the processor, so they become located on an edge where they can be interacted. In both of these cases, the capability is there for the quantum computer to solve the problem. It's just a question of the resources required, especially the number of gates, and whether these can reasonably fit inside the coherence time of the system. It is worth saying here also that a technique exists called quantum error correction that trades off additional physical qubits for an increased effective coherence time. By operating around 10 physical qubits as one logical qubit, we can run circuits with orders of magnitude more gates. This is the future regime of fault-tolerant quantum computation, which will take over as our devices scale past the hundreds and into the thousands of qubits. The final capability of a quantum computer involves solving optimization problems with hard constraints. These are constraints that must be satisfied by the solution and where you can efficiently know some or all valid solutions a priori. An example of this is a parity constraint, where the sum of the binary solution variables must equal some natural number. Note here we're talking about binary variables denoted x with possible values of 0 and 1. This is different from the spin variables mentioned before, but they relate as shown. Which form is most natural depends on the use case. Here, binary variables are convenient to describe a parity constraint. Readout of classical information is similarly always in zeros and ones, the classical bits, but most of the work with gates is in terms of spins because they act on the quantum system. So, quantum computers can do all this stuff, but when is it really going to surpass classical computation? One analysis shows that finding the number of zeros of an at most 3-body Boolean satisfiability problem with unit weights would be intractable to simulate classically, but possible to solve with a quantum computer of sufficient fidelity for instances with 420 variables and 500 constraint clauses. Advantage with respect to best-known classical solvers may exist in other places, and it's a question worth investigating. So, let's look at quantum algorithms for constraint solving. A quantum algorithm defines the quantum circuits to run and includes any classical pre- or post-processing that needs to go around the quantum circuit. We'll start with the Quantum Approximate Optimization Algorithm, or QAOA, which can be used to solve unconstrained polynomial optimization problems. This algorithm uses a quantum circuit, here in blue, inside a classical optimization loop, which is shown in green. The algorithm works on the basis of the variational principle. This tells us that if we build a quantum circuit called the Unzots based on our cost function and these variational parameters, beta and gamma, then we can vary these parameters to minimize the expectation value of the cost function over the bit strings that we sample from the circuit. And this will provide the best approximation ratio and so the best bit strings for solving the input problem. This variational optimization is entirely classical and can involve parameter trials over the beta and gamma parameters to calculate gradients, apply genetic algorithms, stochastic perturbation methods, Bayesian methods, or your favorite optimizer. Further, within the quantum circuit, repeating these circuit parts that we call the driver and the mixer is theoretically proven to improve the approximation ratio, at least in the case of an ideal quantum computer. In reality, deeper circuits accumulate more noise, and increasing P does not necessarily improve performance. For unconstrained problems, we start in a superposition of all 2 to the power of n possible outcomes. We get there using a Hadamard gate, which is realized on Righty hardware as a sequence of x and z rotations. These rotations are changes in the quantum state that you can visualize on the block sphere, a unit sphere where every single qubit quantum state can be depicted using 2 angles, and where the 0 and 1 states are at the poles, representing purely classical information. Any state in between here is a quantum superposition, with the latitude representing the probability of the 0 versus the 1 outcome, and the longitude relating to this thing that we call the phase. Our Z rotation gate works with any angle, while our X rotation gate only works for angles that are a multiple of pi on 2. RZ is also not a physical gate. Its implementation is just an update to a phase tracking parameter in the control system. The RX gate plays a single control pulse down the wires into the fridge and onto the QPU. Overall, this means we can get into a superposition state by playing a single pulse on each of the qubits. The driver circuit, or the driver part of the circuit, aims to separate the good solutions from the bad ones in phase space. Now, don't worry too much if the maths here doesn't make that much sense. Just think of a quantum computer as a giant interferometer whose interference pattern is being programmed to bring the best solutions to the top probabilistically. This phase separation step uses the input problem structure and data to do its job. For a max cut problem, we can design a real valued cost function that tells you how many cuts there are in the graph, given that the vertices are partitioned into those with spin +1 and spin -1. For each edge, this first equation contributes 0 if the spins are the same, which means there's no cut, or 1 if they're different, which means there is a cut, and so overall C counts the number of cuts. There is a systematic process for turning this real valued cost function, written in terms of spin variables, into quantum gates. Constants are promoted to the identity, spin variables are replaced with a Pauli Z matrix, and tensor products replace multiplication. If we consider a single edge, the quantum operator that this defines is of the matrix form shown here. You can see the phase for the bit strings where the vertices are in the same partition, up the top and down the bottom, are different from the phase when the vertices are in different partitions, and so there's a cut. This operation can be realized with a controlled phase, or C-phase, gate on our hardware. It's worth saying that the Righty hardware has multiple 2-qubit gates, and they're all functionally capable of building any 2-qubit operation, but the performance can vary dramatically. The C-phase gate that we prefer to use for max cut needs only 2 pulses on the hardware, while the controlled Z and XY gates require 6 or 10 pulses. When solving max cut problems, it's not too surprising that we get the best performance using C-phase. Within some bounds on the form of the quantum physics supported in the device, there is room to design gates to improve specific algorithms. There is a huge difference today between throwing a textbook implementation of QAOA at a high-level programming SDK and working with the hardware engineers to understand and optimize for your specific use case. This is something that we pursue at Righty as a co-design activity that teaches us what matters for real-world problems and helps the quantum curious get a much more realistic assessment of the state of the art for your specific use case. So, the driver part of the circuit separates solutions in phase, but phase alone does not affect the output distribution of measured solutions. The mixer circuit uses an X rotation, firstly so that some amount of phase separation is seen in the output, and secondly, the mixer is key to letting us repeat these circuit parts to improve the solution. The mixer is chosen to anti-commute with the driver, which means that repetitions of the driver explore new parts of the quantum state space, making it theoretically more likely to find better solutions. QAOA asks that the X rotation be of an arbitrary angle, the beta parameter that we're optimizing over classically. But we don't have continuous angle X rotations on our QPU hardware, so we rotate X to the Z axis, do a Z rotation, and then rotate it back using this sequence. This winds up costing us 2 pulses on each of the qubits. So together, initializing into an equal superposition and running these driver and mixer circuit parts are the building blocks of the quantum circuit used by QAOA to solve unconstrained problems. when we encounter constrained optimization problems, and where we know how to efficiently determine the feasible solution subspace, we can use a variant of QAOA called the quantum alternating operator Unzots. Ideally, the initial state would be a superposition of all feasible states, which is called a Dickey state. But this can take a lot of gates to prepare. A simpler approach, shown here, is to initialize into a single classical solution and then use the mixer circuit with a constant parameter to premix to some non-uniform superposition. The design of the mixer circuit itself here is specific to the type of the constraint, and it will assume additional data from the input problem. In the previous section, we presented the parity constraint. We can implement a mixer circuit that realizes this constraint directly using the XY gate. Now the mixer is operating on edges, not vertices, and so it's a 2-qubit gate, not a single qubit gate. The XY gate is parity preserving. What it does is exchange some amount of population between the 0, 1 and 1, 0 states, but it leaves 0, 0 and 1, 1 alone. That means it exchanges population between the two states that have a parity of 1. Having initialized the system into a state with the right parity, doing this over all the edges in the problem graph allows the quantum system to explore all feasible solutions that preserve the parity. Of course, on real hardware, the XY gate is imperfect, so some population does transfer to infeasible solutions. However, overall, there's a preference for feasible solutions, and so this type of advanced mixer is sometimes beneficial compared to the unconstrained approach, where many infeasible solutions may have to be discarded. So, these two algorithms that we collectively call QAOA are the main two that you'll see in the literature. There are other variations on this theme, but it suffices for today. What I'd like to do next is show you these algorithms in action on the Righty QPU, solving an example max cut problem. Here we are in the Righty Quantum Cloud Services environment. In this environment, you can book time on the Aspen 9 QPU, as I have done, access some starter tutorials, and run programs in a Python notebook environment called JupyterLab. And this is where I'm going to be running today's demo. I've prepared a demonstration notebook which creates a code-level connection to the Aspen 9 QPU and its supporting services. We can get topology and fidelity data from the device, and I'm using that information here to render a simple image of the available qubits and their edges. Getting a program onto the QPU through Quantum Cloud Services happens in a sequence of operations designed to give you, the user, control of the process at each stage. I'll illustrate this flow for an example of a Bell state circuit, which is depicted here. A Bell state is a circuit that uses entanglement to ensure that whatever value is measured on the first qubit, the same value is measured on the second one. We start with a logical description of the circuit operations. These use gates that you'll see in the textbook. Here, we have Hadamard and CNOT gates. The circuit can be described using QUIL, our quantum instruction language, which defines the initialization, gate operations, and measurements to be performed. QUIL can be described in text, like you see here, or it can be generated programmatically via our Python binding called PyQuil. A compilation process converts this QUIL into native QUIL, using the processes shown earlier of injecting swaps to map interactions onto the available edges and decomposing these logical gates into hardware native ones such as RX and RZ. In the simplest case, this native program can then be transformed into a binary ready to be run on our control systems, and then executed to generate one or many measurement results. When we do this, the control sequence used for each native instruction is determined using our production calibration database. But we aren't limited to these. QUIL-T lets us take control of the time domain analog behavior of our QPUs by specifying calibrations, frames, and waveforms that describe the pulses and their timing for each of these native gate operations. While we won't use these in this demonstration, it is this kind of level of control that allows us to optimize on a use case basis and not rely on a one-size-fits-all set of production calibrations. So let's run the Bell state circuit. Here we first declare the Bell state program using PyQuil, which you can see the output here. We then compile it to the Righty native gate set, which gives us a result similar to the one above. We then transform that into a binary that's ready to run on the control systems for the QPU. And then we can actually run on the QPU. Now, as this runs on the ASP.9 device, it's going to return an array, a 2D array, of measurements. It'll be 2 across by 10,000 down because we asked for 10,000 samples, and they're 2 qubits wide. We can take this array of results and analyze the outcomes, plotting them in a histogram. Here you can see the expected states for a Bell state, 0, 0 and 1, 1, with the correlated measurements, are dominant, but there is still some population of 0, 1 and 1, 0, and this is due to the infidelities in the gates. Now, the native program had a CZ gate in it, which was the entangling gate. If we want, we can look to understand the time domain behavior of this CZ gate by looking at its calibration. Here we can see that a CZ gate is performed using one pulse and several updates to phase tracking parameters across the control system. The fence directives that you see here tell the control system to globally synchronize across all qubits in the system. And this has the effect that this pulse is played with no other pulses running in parallel. And this is a way to maximize the fidelity of this particular gate. If we want, we can also look at the waveform, the pulse waveform that was associated with this particular gate. We can see that here. So let's move on to our demonstration of solving max cut problems using QAOA. So here we'll define a simple 7-node max cut problem on a linear graph, for which we know that the maximum cut is 6, which is the number of edges. We'll implement the QAOA algorithm directly using Righty native gates, consistent with the material that we presented earlier. This means we've picked a linear chain of qubits on ASP.9, and you can see the edges that we've picked here. So this brings us to the programmatic implementation of QAOA. Here I've omitted the variational optimization, which I ran before starting this demo, in an appendix at the bottom. This is because that part can take several minutes to complete, and today we're focusing on the quantum hardware. So I already have good beta and gamma parameters to use. So within this implementation, we first declare the variational parameters, beta and gamma. We run the decomposed Hadamard gates, which puts us into a superposition of all the different solutions. Here we have the phase separation operator using C-phase. which runs over all the edges of the max cut problem. And then we have the X rotation, the mixer, which we use so that we can measure the outcome. And finally, we actually have the measurements. Now, this is for a p=1 circuit. If we were aiming to have deeper p, then we would have put a loop around the phase separation and the mixer operators so that they were repeated in the circuit. We've asked here for 10,000 samples to be generated. We have our parameters, and we've compiled and run using those parameters to get the results. Now note here that what you're seeing is parameterized compilation and execution in action. What we can do here is we can compile this program all the way to the binary executable once, even though it has some unfilled parameters, and then we can execute it, trying for many different values of these parameters in situ. This way, we can be done with an optimization problem in minutes rather than hours, because we compile once and then rapidly execute across all the different parameters in rapid succession many times. Again, we can plot a histogram of the results. You can see here that there are only 2 optimal solutions out of the 128 possible for a 7-node problem, and these have been highlighted. You can see they are some of, if not the most probable solutions out of all the solutions that were returned. By chance, we would have only found these 2 solutions 1.56% of the time, but in this particular run, we found them nearly 7% of the time. The optimal solutions have an alternating pattern of zeros and ones in their solution bit string. Each node in the linear chain must be in a different node set to maximize the cut. One of the optimal solutions starts and ends with a 1. It's 1, 0, 1, 0, 1, 0, 1. While the other one starts and ends with a 0. Hence, one of the optimal solutions has 4 ones, and the other one has 3 ones. So what we might try and do here is add a constraint using an advanced mixer, a parity constraint, to ask for the solution with 4 ones. In this updated program, instead of a Hadamard, we place the 4 of the qubits in the 1 state, which gives us the target parity, and then we premix with the XY gate, and a constant mixing parameter of pi on 8, which we choose arbitrarily. The phase separation operator is the same, but then the mixer is also replaced with a beta parameterized XY gate over all the edges in the max cut graph. All the rest is the same. Again, we can run this on the QPU using some optimal parameters that I selected earlier. When we plot them with a histogram, we'll see that the valid solutions, in terms of the hard constraint, are shown in purple, and the optimal solution that we were trying to extract is again shown in teal. In this case, we've recovered the optimal solution 1.35% of the time, which is better than guessing. And in terms of the validity of the solutions are valid about 21% of the time, whereas guessing would be 27% of the time. For interest, if we want to, we can actually go back all the way to the top and see what happens when we run on a simulator. We can do this by specifying a virtual device. We see the Bell state example gives us exactly the right probabilities. We see a similar, though slightly boosted result for the unconstrained case. And we see the reference result for our hard constraint implementation, which also has the valid solutions dominating 100% of the time there's no invalid solutions, which is what you would expect. But the solution we're looking for is not dominant. So we sort of see that we have a possible issue with our implementation here, that the pre-mixing and the way we've implemented the hard constraint could be better. And that's pretty normal for implementing quantum algorithms on quantum computers. In this last section, I'd like to conclude the talk with some highlights of recent work that we've done at Righty to develop our first 3-qubit gate, and the application of that gate to the max 3-stat problem. Max 3-stat is an interesting constraint satisfaction problem near the root of Karp's complexity hierarchy. Solving max 3-stat on a quantum computer requires the same process as outlined before, where we can engineer a spin system cost function for a single clause of the form shown. For the 3 literals in any clause, there's a choice to negate or not negate the literal, and this will select whether or not a plus or a minus is used in each part of this expression. Overall, there's 8 permutations of 3 variable clauses that can be made for each constraint. If we pick the example of the clause that contains 3 negated variables, so not x0 or not x1 or not x2, we can write out the expanded cost function here and its truth table. So we can see that the cost function correctly encodes the expected clause outcome. We have the cost function providing 1 when the clause is true, and it equals 0 when the clause is false. If we convert this clause to a quantum operator, as we did for maxcut, then the 8x8 unitary matrix will phase separate the 7 cases where the clause is satisfied from the one where it is not. The matrix on the right, which is equivalent up to a global phase, is the textbook controlled phase gate, or CC phase. Note that in a quantum computer, global phase cannot be measured and has no effect on the outcome. So from an operator's perspective, the CC phase gate is exactly what we need to phase separate solutions for our example clause. Given that our physical connectivity on the Aspen9 processor is only edge connectivity, it's a good question to ask, how do you do 3-qubit gates with that? A 3-qubit state has 8 basis states. You can plot them on a cube like we show here in blue. The first thing we do is promote one edge, shown in green, to the 2 state. This is the second excited state of the qubits. Now normally we only use the ground state, 0, and the first excited state, 1. But a qubit, physically, has many more excited states. If you can control them, then you can pull this kind of trick. We next do the same thing on this back edge, except that now we've moved one of the affected populations out of the way. So in effect, we're just promoting and then bringing back down with a user-defined phase, just one state, the red one, out of the original 8. We can then fold back the stash states and we've completed our 3-qubit gate and we're done. As you can see here on the right, this gate achieves good linear control over the continuous angles, which means we can drop it straight in as the phase separation operator in the variational QAOA algorithm, and it will give us the phase separation we need for a clause of max 3-stat. In the paper that we reference here, we showed significant improvement in fidelity for a max 3-stat clause using CC phase compared to decomposing it down to its 1 and 2 qubit gates. By having this type of gate in our arsenal, we can come back and look at any other constraint satisfaction problem with up to 3 variable interactions, and we have some tools to achieve improved performance. So thanks for your time. I'm happy to answer any questions during our Q&A, or for anyone to get in touch to discuss how Righty can help support research and development of quantum solutions to constraint satisfaction and other optimization problems.